In this lecture video, we will go over hydration reaction, which is the second type of addition reaction of an alkene. And in the course of this reaction, a hydrogen and a hydroxy group are being added across the double bond. We can either have the hydrogen being added to the carbon 1 and the hydroxy group added to the carbon 2 to produce this product right here. Or we can also have the other way, where the hydrogen is then being added to the carbon 2 and the hydroxy group is added to the carbon 1. Please take note that the hydrogen and the hydroxy group are actually not from the same molecule, water. But then hydrogen is being added through one reagent and the hydroxy group come from another chemical substance. But we call this hydration reaction because overall water, a hydrogen and a hydroxy group are being added to the double bond. And there are three different ways or three different sets of reagent how we can add water across the double bond. And each of this method right here have different reaction mechanism. Regioselectivity, as what we have seen above, do we form this product more or this product? So that is the regioselectivity. And the stereoselectivity, because initially carbon 1 and carbon 2 are not chiral, but now as we produce the product, they may become chiral center. So are there any stereoselectivity at all? We will also be discussing that as well. And there can also be carbocation rearrangement as well. So each of these different ways right here would offer us different control, whether it is regioselectivity, stereoselectivity, or carbocation rearrangement control. And the three methods are known as follows. First, acid-catalyzed hydration. And method B, oxymercuration-demercuration. And third method, hydroboration and oxidation. So these are the three different ways how we can add water across the double bond. Let's now discuss the first one. First, acid-catalyzed hydration. So this is the types of reaction where a strong acid is being used to catalyze the reaction. And now, it's not just any strong acid, but it has to be a strong acid in which its conjugate base is a weak nucleophile. And so this basically makes the binary acid not fall in this list, because the product of binary acid, their conjugate base are the halide, for example, chloride and iodine. And we can see that this is a good nucleophile right here. So therefore, HCl, HBr, or HI would not be the strong acid that we can use here in this case. Most of the time, that strong acid is sulfuric acid, because the conjugate base of sulfuric acid is hydrogen sulfate, and that is not a good nucleophile. So that's the requirement right there. It has to be a strong acid in which a conjugate base is a weak nucleophile. And overall, here is the scheme of this reaction. So in this case right here, we have discovered the following. In acid-catalyzed hydration, the regioselectivity of this reaction is as follows. The OH group is actually added to the more substituted vinyl carbon. So in this case right here, the carbon 1 is more substituted than the carbon 2. And now the hydroxy group is added to the more substituted carbon. And the hydrogen is then added to the less substituted carbon. And this is the regioselectivity in acid-catalyzed hydration reaction. And this most of the time, this reaction right here proceeds with about 90% yield. And this product again is called the Markov product. So we basically extend the definition of Markov here in this case, in which that the hydrogen is added to the less substituted carbon, or the X or the hydroxy group is then added to the more substituted carbon. So this is basically an extension of the Markov definition. And we call this the Markov products or the Markov addition. And the mechanism of this reaction is as follows. So let's say we draw out a structure of a generic alkene. So let's say this alkene, and now when we treat this with acid. So first here we have sulfuric acid. And the alkene acting as a base come in to pick up one of the proton from the sulfuric acid. And now in this case right here, it would be the less substituted carbon that have the hydrogen added to it. And the reason why is we want to put the carbocation on the most substituted carbon, so that way it will become more stable. So this is a tertiary carbocation, which is more stable, and that's why the major product would be the product that go through this more stable intermediate. And once we have this already, we also have water in the reaction, and that is our nucleophile. So water is nucleophilic. It is not a good nucleophile, but in this case, since we have such a great electrophile, it will make it possible for water to come in and attack it and producing this product. And lastly, to neutralize this product, we can have another water molecule behaving as a base, come in to neutralize, pick up this proton, and neutralizing our organic products. So that's what happened in the course of this reaction. And again, the hydroxy group is added to the more substituted carbon, and the hydrogen is added to the less substituted carbon. And that would then be our products. And it is called the Markov products. And we have observed that the rate of an acid-catalyzed hydration reaction is very much dependent on the structure of the starting alkene. So here in this case right here, the relative rate of these three different alkenes in acid-catalyzed hydration in comparison as follows: 1 to a million and 2 times 10 to the 11th time. And the reason why is that in this case right here, this alkene right here is more substituted, and because it's more substituted, it then goes through a more stable intermediates, and therefore it have a faster reaction rate. So this have more stable intermediate. And hydration reaction is basically is a very effective method to basically convert an alkene into an alcohol. And now, as for controlling the position of equilibrium, we can see already that the addition reaction and the elimination reaction are in equilibrium with each other, and we can actually control whichever direction that we want by utilizing the short-lived principle. So here in this case right here, go in this direction from the reactant into the product. This is addition reaction. Versus the opposite here would then be elimination reaction. It has been found as follows. If we were to use diluted sulfuric acid, that would then favor the addition reaction. And again, we want to also do this at low temperature as well. Versus if we were to do the opposite, the elimination reaction, we will be using concentrated sulfuric acid. And we'll be doing this at high temperature. So why the diluted sulfuric acid favor the addition versus concentrated sulfuric acid favor the elimination? The reason why as follows. We can see that water is a reactant in the course of the addition reaction. So the less sulfuric acid that we have, that basically means the more water we would have. And now the more reactant we have, we will be able to push equilibrium to the right side, and in this case undergoing the addition reaction. And the opposite would then be true, that if we were to use concentrated sulfuric acid, this basically means less water is present, and therefore it would be basically favoring the elimination side. And again, we also need to do this at high temperature as well. So by controlling the concentration of the acids and the temperature, we will be able to favor whichever direction that we want, whether we want to do addition or elimination. And now let's discuss the stereochemistry control of acid-catalyzed hydration. So the stereochemical outcome of an acid-catalyzed hydration is very similar to the stereochemical outcome of a hydrohalogenation reaction. There's no selectivity and a racemic mixture is being produced. And the reason why is that, as we analyze the reaction mechanism, it goes through a carbocation intermediate that is achiral. So therefore, when water comes into attack, water can either attack from the top or from the bottom without any preference at all. So therefore, be able to form both a product where the hydroxide could be pointing up or pointing down, and thus they are mirror image of each other, or a racemic mixture. So here in this case right here, if we were to perform this reaction, we'll get this following product. And again, this is the most substitute carbon, and that where the hydroxide group will be added, and the hydrogen will then be added right there. So in this case right here, we can either have water, hydroxide group pointing up, and now that would then make this metal point down. And the other enantiomer, where the hydroxy group is pointed in the back and the methyl group is in the front. We will form a 50% of this, or a racemic mixture. And now let's try some of the practice problems. So here's the problem. Identify whether you would use diluted sulfuric acid or concentrated sulfuric acid to achieve each of the following transformation, and in each case explain your choice. So here in this case right here, we are trying to do addition, because going from the reactant as an alkene into the product side, and in this case right here we can see the hydroxy group is being added to the more substituted carbon, so that is the Markov product right here. So therefore the reaction will be very straightforward. This is an addition reaction, and to do addition reaction, we would then need to use diluted sulfuric acid, and again low temperature as well. The low temperature is very much needed anytime that we need to do the addition reaction. And now, as for the second example, here in this case right here, this is an elimination reaction. So in this case, we will then have to use the concentrated sulfuric acid, and we also need to perform this at high temperature. And now we will discuss the second method of doing hydration, the oxymercuration-demercuration method. So again, this is a non-efficient method of converting an alkene into an alcohol. And in the oxymercuration-demercuration method, then it will also add the hydroxy group to the more substituted carbon. So basically, it will do a Markov addition of water across the double bond. And now the advantage of the oxymercuration-demercuration method is that it will perform this reaction right here will not undergo carbocation rearrangement. Carbocation rearrangement will be a problem that we would observe with the acid-catalyzed hydration. But here in this method right here, there will be no carbocation rearrangement. So initially, we would then take our alkene, react this with a reagent as follows. And once we have done this, what will happen is that the hydroxy group will then be added to the more substituted carbon, and there will be another group, the mercury group, that will be added to the other carbon. So that's what happened in the oxymercuration step, followed by the demercuration. So in this case right here, we will be using sodium borohydride as the reagent. So this is the second step. And when we do this, now the hydride will come in and replace this silver or this mercury group right here. And in this case, right now, this is what we're going to have. So this is the demercuration step right here. And we can see that the product here would then be the Markov product. And this reaction proceeds without carbocation rearrangement. And the mechanism of this reaction is as follows. First, the oxymercuration step. So that is the first step right here. So this process right here begins when the mercuric acetate dissociate to form the mercuric cation first. So the reagent consists as follows. So that is the mercuric acetate, and the mercuric acetate basically first broken off to form the following. And this mercury then become a carbocation plus the acetate group. And now this mercury right here, it become a good electrophile because it's it is a cation. So in this case, this is a good electrophile. And because mercury can exceed octet, therefore it can accept the external electrons. And once we have formed this mercuric cation right here, it becomes a good electrophile, and that is then subject to attack by the pi electron from the alkene. So let's say here is our alkene. And now once alkene come in to interact with the mercuric acetate, the alkene would now become a carbocation. And in this case, it would be the mercury group will be added to the less substituted carbon, so that way we can produce a more stabilized carbocation. And the mercury will be added right here. Now, once we form, so this is called the mercurinium ion. It is called a mercury. And once we form this ion right here, what will then happen is that because the mercury also has a lone pair of electrons on it, and that what make it a good nucleophile. And here in this case, we will then come in and attack this carbon right here to form a 3-member ring, producing this product as follows. And now the mercury become a carbocation. So this is what we'll be producing right here. And because of this process right here, where now it is the mercury that now become a cation, therefore it do not undergo rearrangement. So this would then happen immediately before this carbocation right here could rearrange. And that's the step that prevent the rearrangement of the carbocation. And now once we have this already, then now this again it become a good electrophile. So if let's draw the structure of the mercurine ion again. So in this case, this is what we have. So that's what we have right here. And here in this case, when we do analysis of this, we will then see as follow. This 3-member ring right here, and again, as we have learned before already, 3-member ring are not stable at all. And in fact, this ring right here is ready to break apart. And in this case right here, before it actually can break before even something come in to attack it. So here in this case, this is actually ready to be broken. And it can break as follow, where the electron come from this bond right here and come to the mercury, or the electron from the other bond will then come to the mercury. So in this case right here, it can either be this carbon right here or this carbon that will be given the electron to this mercury ions to break this 3-member ring apart. And here in this case, since this carbon right here is more substituted, it is more electron rich, and therefore is more willing to donate the electron to the mercury, making this positive polar charge on this carbon right here a whole lot more positive compared to the other carbon. So therefore, as we have our nucleophile, here in this case right here, water is our nucleophile. Or we can also have any other types of nucleophile that will be able to come in and attack this carbon. Now notice how the nucleophile, in this case water, is attacking the more substituted carbon. And again, it attacking the more substituted carbon because this carbon right here donate electron to the mercury as this ring is breaking apart already. And in this case right here, we'll be producing this product. So the nucleophile or water will then be added to this direction, and this ring will break apart, and we now have this mercury acetate over here. So at the ends of this oxymercuration step right here, this would be the product that we'll be producing. And followed by the second step. So this will be the product of the first step. The second step is then the demercuration step, which is basically accomplished by reacting with sodium borohydride. Now sodium borohydride is a very good source of hydride that are nucleophilic. So here in this case right here, we would have the structure of sodium borohydride is as follows. So the boron would then donate electron to one of this hydrogen, and therefore that becomes a good source of hydride acting as the nucleophile. So the good source of hydride. And now the hydride from the sodium borohydride will then come in, attack this group right here, and kick off this group. And therefore in the product, this is what we're going to have. So our nucleophile, whatever our nucleophile here would be. And as for the other group, we now have the hydrogen over here. So that would then be the product right here. And if our nucleophile is water, then now we have the OH group over here. And that's how we can convert an alkene into an alcohol. Now, so depending on the nucleophile, the many different products can be produced by choosing the proper alcohol. If we were to want to do hydration, then our nucleophile would then be water. But in addition to water, we can also substitute that with another types of nucleophile. So here in this case, any types of nucleophile that we want. If we want to do hydration, then this would then be water right here. And in this case right here again, the nucleophile would then be added to the more substituted carbon, and the hydrogen is then added to the less substituted carbon. And that is the regioselectivity in this oxymercuration-demercuration method. And again, the product would then be considered as the Markov product. Let's now try a few examples. So here in this case right here, if we were to take this alkene and react this with silver acetate in the presence of water, so water would then be our nucleophile, followed by the demercuration step. Then again, what would then be the product? So again, we would then see that it would be a hydration reaction. And this would then follow Markov, where the OH group is then added to the more substituted carbon. So make sure we have that worked out first before we write out the structure of the product. So here in this case, that would then be water. And as for the example number 9, then here in this case again, this again follow the Markov addition. So therefore the OH group will be added to the more substituted carbon. Now, so notice here in this case right here that this carbon right here is a chiral center, and there's no stereoselectivity in the oxymercuration-demercuration method. So we will be then producing the other and enantiomer. So it will be producing a racemic mixture. And now with 10, then very much the same thing. Again, the OH group will then be added to the more substituted carbon, and that will then be this carbon. So the product would then be as follows. And as for number 11, here in this case right here, we are not adding water, but we are adding ethanol. So in this case right here, ethanol will be able to add in methyl-ethoxy group to the carbon. And in this case, will be this carbon right here. And now this become an ether. So if we were to use an alcohol, we'll be able to convert an alkene into an ether. And similarly with this reaction right here, if we were to use ethylamine as our nucleophile, so here in this case we'll be able to convert this into an amine. And now we will discuss the third method of doing hydration. So in this case right here, we call this the method the hydroboration oxidation method, or simply hydroboration. And in this method right here, it will do an anti-Markov cup addition of water across the alkene, where the hydroxy group is actually added to the less substituted vinylic carbon on the alkene. So here in this case, if we were to be looking at this alkene right here, the OH group would then be added to this less substituted carbon right here. And on the product, that is what will happen. The OH group will be added right there, and the hydrogen will then be added in here. But this method right here is a two-step method, where first we will do a hydroboration first using BH3 and THF, so that is the chemical reagent for it. And initially, when we just do the hydroboration step, the product that we will be making will be as follows. We'll be putting the BH2 group in here and a hydrogen in here. And once we obtain this intermediate already, we then follow with the oxidation step, where we will then be using the hydrogen peroxide in the presence of sodium hydroxide. And that will then convert this BH2 group into the OH group. And that's the product that we'll be getting toward the end. So again, it is a two-step method. Now, so in the hydroboration method, it is stereospecific, but not completely, in which that we have observed that the hydrogen and the OH group are actually a curve in which they're adding to the same side of the double bond. And we refer to this as the syn addition. So syn here means the same. So the two groups are being added to the same side of the double bond. So here in this case, if we were to draw the product of this reaction, we would be obtaining the following. So again, the hydrogen is then added to the more substituted carbon. And now the OH group is then added to the less substituted carbon. And in this case right here, they are both pointed on the same side of the double bond. That's the meaning to this syn addition. We can also form the other products. And the other product would then be the other enantiomer, where now the hydrogen is pointed in the back and the methyl group pointed in the front. And here on the other carbon, the hydroxy group are also pointed on the back as well. So that's what happens. In this, they are an enantiomer. So we are still producing a racemic mixture, but we do not produce any diastereomer. So no diastereomer. The diastereomer would be the other product where the hydroxy group and the hydrogen are pointed on the opposite direction, and we do not observe that. But again, we are making a racemic mixture of these two enantiomer only. So that provides some sort of stereoselectivity right there. And now let's first talk about the reagent first. Because in order to understand this reaction right here and why they produce this product right here, we need to understand how did the reagent work out. So the first reagent is the borane. Borane is basically BH3. And this behaves very much similar to a carbocation, except that it did not have a charge on it. So when we draw out the structure of borane, this is what they would look like. And as you can see, that the structure of this, it is basically sp2, that the hybridization of the boron, and now it actually have a p orbital on it, and it would then behave very similar to a carbocation, in which that this can accept electron. So we can actually have, if we were to have a reagent that is nucleophilic, that would then be able to donate electron into this p orbital right here on the borane. So this borane right here is electrophilic. very much similar to a carbocation carbon, except it may not be as reactive. And the reason why that this have a positive charge on it versus this is neutral. Now, once a nucleophile come in to react with this borane already, this is what it would then become. And now there will be a negative charge on this borane. So notice how this negative charge right here locate on the boron. And because boron have low electronegativity, once it become negative already, it actually is not very good in holding on to an electron due to the fact it have low electronegativity. So therefore, it would then donate the electron to one of these hydrogen right here. And that's why it become a source of hydride. So it can produce a lot of hydride. So that's the chemistry of the reagent. The BH3 is basically a good source of the hydride. And now let's talk about the mechanism of how did this work out right here. So here in this case right here, when we take the alkene and we react with BH3, so our alkene here will be serving as the nucleophile. And that would then come in and attack the boron. And then producing this product as follows. Now, the reason why that this hydrogen and the BH2 group are added on the same side is as follows. So let's say that if we were to be looking at this structure, draw the mechanism of this. When this come in to interact with the BH3, so here is the BH3. First, the alkene will come in and attack this boron to form a bond to the boron. And as that happens, this carbon right here will then become a carbocation. And once this become a carbocation, and now we can see that the boron now become negative, so it then give the electron to one of this hydrogen. And this fall off as a hydride. And this hydride right here come in to attack this carbocation right here immediately. And because of this positioning right here, therefore the BH2 group and the hydride are added to the same side of the double bond. And what we now be producing is as follows. So we can have the BH2 group in the front and the hydrogen be added to the front as well, or both of the group are added to the back. But then that is the product that we would get. And this step right here, once we have produced this already, then notice how this go back to BH2 again, and it basically become a good electrophile in which that another alkene can come in to react with this again. So this step right here can repeat 2 more times. Because one of the molecule of one of this boron reagent can react with up to 3 of the alkene, and in the product, this is what we'll be getting. So and now we're just gonna simply abbreviate each of this as an R group. And that's what we'll be producing. So at the end of the hydroboration step, this will be the product of what we are making right here. And again, the alkene is now part of this R group. And on the second step, we would then be taking this reagent right here and reacting this with the hydrogen peroxide. And this step right here is then called the oxidation step. And in this oxidation step right here, the product that we'll be producing is then as follows. So the OH group is replacing this BH2 group right here and producing our alcohol. And the mechanism of this reaction is as follows. So first, we have hydrogen peroxide. And in the presence of sodium hydroxide is a good base. It will then come in and pick up the proton from this hydrogen peroxide, because this pK right here is about 12. So that come in and pick up that proton and converting this into this product. And once we have produced this product already, this will now become a good nucleophile. And that will then come in and react with our boron, come in and attack the boron again, producing this product. And now there is a negative charge on this boron. And again, once boron it becomes negative already, it's not very well stabilized because it have low electronegativity. So what would then do is that it would then give the electron to one of this R group, and this R group will then come in and attack the other oxygen directly and kick off this OH group. So that's the mechanism right there, because this OH group right here, it is an OK leaving group. So we can imagine this taken off, making this oxygen right here do not have an octet of electron and become positive. So therefore this become a good electrophile. So the R group would then take the electron from the boron, come in and attack this oxygen right here. And now following this arrow right here, we'll be producing this product. And we have another hydroxy group falling out. And this step right here would then repeat again. So this hydroxy group come back and pick up another proton from another hydrogen peroxide to produce this again. So more of this would then come in and attack this again. And this process right here would then be repeated 2 more times to ultimately produce this product. And once we have this 3 group already, we still have hydroxide in the reaction, and that will then come in and attack this and kick this, and now kick off one of this OH group. And this will then keep on happening until we produce the following. So now we have and now one of our OR group is now falling off, and this can now come in. Now the R group in this case right here, that is our cyclohexane. So basically the structure of this is as follows. And now in this case right here, this oxygen right here point up and the hydrogen is pointed up as well. So that is the structure of the R group. And once we have produced this already, this now can act as a base, come in and pick up another proton from water and producing our product. And that's how we produce this product right here. So the mechanism is quite lengthy, but then that's how the product works out. And again, one thing to notice is that this is an anti-Markov addition and also syn addition as well. So this is anti-Markov and syn addition, in which the hydrogen and the OH group are added on the same side of the double bond, and we will be making a racemic mixture. But we do not produce the other diastereomer. Let's now try some of this example right here. So in this case right here, we are taking this alkene and we do a hydroboration. So that's the first step, followed by the oxidation step on the second step. So what would then be the products? And again, recognize that this will do the anti-Markov, meaning the hydroxy group will then be added to this. Let's substitute the carbon right here, and the hydrogen will then be added right there. So here in this case, our product will then be as follows. And we also have to take notice that this is a syn addition. So basically the hydrogen and the OH group are then added to the same side. So that is one of the enantiomer, and will form the other enantiomer where both the hydroxy group and the O hydrogen are pointed on the back as well. But then that would be the product right there. And let's now try another example, 14. So here in this case 14 right here. And again, by seeing the reagent, we know that this is a hydroboration followed by the oxidation. So here in this case again, this will then undergo the anti-Markov addition, where the OH group will then be added to the last substitute carbon, and the hydrogen will then be added right there. So in this case right here, we'll be producing this product. Now, since this carbon right here is not a chiral center, so therefore we don't have to show the location of the hydrogen. But if we do, then we will see we can put the hydrogen in, and that be pointed in the front as well. And we'll form the other enantiomer where both of this group are pointed in the back. But again, we don't have to specify this hydrogen since this carbon right here is not a chiral center.